Okay, welcome to Obstructing Lagrangian Concordance for closures of three braids, part 2. If you haven't seen part 1, please go watch that video because this one won't make any sense. Thanks again to the organizers for the invitation to speak. Okay, so you'll recall where we left off in the last video. We just obtained an open book decomposition of the double cover of the transverse push-off of lambda. This open book decomposition has punctured tori pages, and the monodromy of this open book decomposition is given by a Dane twist about the curve alpha and about some PQ curve, which we call gamma. So for the 10-155 knot, alpha and gamma are pictured here, and gamma is a 2-5 curve. Okay, so now what we're going to do with this open book decomposition is we're going to construct a Weinstein-Lefschetz vibration out of it by attaching handles along the lifts of the vanishing cycles corresponding to alpha and gamma in a generic fiber F. And this Weinstein-Lefschetz vibration, which we construct in this way, will be a Weinstein filling of the double cover. And what we're going to do next is we're going to draw its Weinstein diagram using the following procedure of Casals and Murphy. So the proposition that we use is the following. It's quite technical. If you want to read it carefully, you can pause the video. But I'm going to sort of illustrate what we're actually using it for. So if I have Lagrangian lifts of Lagrangians L and S in a generic fiber as follows, then if the monodromy of the Weinstein-Lefschetz vibration is given by tau S of L, then the Lagrangian lift, lambda tau S of L, slash the Weinstein diagram of the Weinstein-Lefschetz vibration is going to be given by the following. So we have the curve lambda L, so the Lagrangian lift of L, and then we're going to have two parallel surgery curves along lambda S, a -1 and a +1. And this sort of diagram is a picture of lambda tau S of L. This is a picture showing the monodromy of the open book decomposition. And what we have to do now is we have to simplify it, get rid of the -1 surgery curves to make it a Weinstein diagram. So we're going to do some simplifications here. I've done a handle slide and a handle cancellation, and what I end up with here is the Weinstein diagram for the Weinstein-Lefschetz vibration, which depicts the Lagrangian lift of the curve tau sub S of L, which is L Dane twisted by S, Dane twisted by Dane twist along S. So basically, what this proposition of Casals and Murphy tells us is a way to translate Dane twisted curves into a Weinstein diagram. And in their paper, they actually outline a procedure, and I'm going to sort of state the relevant steps of the procedure in this case. So we're given the braid word, sigma 1b, sigma 1b inverse. Now we want to find the Weinstein diagram for the Weinstein-Lefschetz vibration. And so first what we're going to do is we're going to find the Lagrangian lifts of alpha and beta. And for us, they are pictured here. They're just going to be these canceling curves of these one handles. The next thing we're going to do is we're going to write alpha and gamma as Dane twists, tau alpha and tau beta, about alpha. And since gamma has slope PQ with 0 less than P less than Q, then actually the Euclidean algorithm is going to give us a word in terms of these Dane twists. So gamma is going to be equal to some sequence of Dane twist tau inverse of beta and tau alpha about the curve alpha. Then what we're going to do is we're going to apply the proposition repeatedly to obtain the Lagrangian lift of gamma. And we're going to draw the Weinstein diagram, which has the attaching spheres, lambda alpha and lambda gamma. And then we're going to simplify the diagram using Lagrangian Kirby calculus. And the result is that for any alpha and gamma, where gamma is a PQ curve with 0 less than P less than Q, the procedure was going to yield the Weinstein diagram depicted here. So it has one handle, one two handle. The two handle enters the one handle with Q strands, and there are P strands, P overcrossing strands. So this is the handle decomposition of a Weinstein filling of sigma 2 lambda, and we'll call it X sub lambda. And we'll call this green and blue curve, or this green and blue knot going through the one handle, d lambda, not so as to not confuse it with lambda, the curve that we're obstructing, sorry, the knot that we're obstructing from concordance. So let me just illustrate what the procedure is doing using the 10155 example. So X sub 10155 has monodromy given by tau alpha and the following Dane twist. So tau about this curve, which is gamma. So gamma is a curve of slope 2, 5. And so what we're going to do is we're going to apply the proposition. So the Lagrangian lift of tau beta inverse of alpha is given as follows. We draw in lambda of alpha, and then we draw in this Dane twist, and then we simplify, and we get this diagram. All right, now let's perform an additional Dane twist about alpha. So we get tau alpha of tau beta inverse of alpha. We will do some handle slides, some cancellations, some Rademeister moves, and we'll end up in the following diagram. Now let's do this one more time. So we're going to do two Dane twists about tau beta, so left-handed Dane twists about tau beta, so tau beta inverse twice, and the result after some handle slides, cancellations, Rademeister moves is the following. Okay, so this is going to be our Lagrangian lift of gamma. And so drawing everything together, we have that this is going to be the Weinstein diagram of the Weinstein-Lefschetz vibration. It has the Lagrangian lift of the handle that we get by attaching along alpha, and the Lagrangian lift of the handle that we get by attaching along gamma. And we can simplify the diagram. So we do a handle slide, cancellations, and then some Rademeister 1 moves. And what we end up with is this diagram, which has 5 strands coming through the one handle and 2 overcrossing strands, for gamma is equal to 2 over 5. Okay. So that's the end of part 2 of the proof, and we can move on to part 3. And part 3 is where we're mainly going to be proving the following theorem. So for lambda as above, as in quasi-positive, algebraic length 2, 3 braid. So for lambda as above, X sub lambda has non-vanishing symplectic homology. So the strategy here is we're going to use the Chekhov-Elyashford DGA to find an explicit non-trivial representative of the symplectic homology of X sub lambda. So the Chekhov-Elyashford DGA is something that we can compute from a Lagrangian link. It's a Lagrangian link invariant. It's generated by Rabe chords. So in our case, we're going to be looking at the diagram, the Lagrangian knot in the diagram with the one handle. So we're going to be looking at Rabe chords, which come from the crossings, as well as Rabe chords from the internal inside the handle. So inside the one handle, there are going to be Rabe chords, and those are going to generate an internal DGA. And the differential of the differential graded algebra is going to be generated by a count of immersed disks with corners at the Rabe chords, the crossings, or inside the one handle. So let me show you an example or some examples. So here again is the 10-155 curve. I've taken the diagram we saw before and I've drawn it in the Lagrangian projection by adding a half twist. This was written down in a paper by Ekholm and Ng. And you can see that this is just the previous diagram plus this additional half twist here. So what do the differentials look like? Well, let's take a look at, for example, the differential of A. We see that this is given by a single disk, which is represented by C0 of 2, 3, and I can illustrate the disk here. So the disk starts at the corner A, and then it has a second corner at the one handle from 2 to 3. So that's why this is C0, 2, 3. Similarly, we can take a look at the differential of B1. So this has a C0 of 1, 2. This comes from the disk that has one corner at B1 and another corner at the one handle from this first strand to the second strand, so from 1 to 2. So this disk is represented by this C0 of 1, 2. And then we also have a second disk, which is T times C0 for 5. So this T is given by passing over this marked point, and we have a corner at the one handle from this fourth strand to the fifth strand. So that's the C0 of 4, 5. Okay, and the rest of the corners are given in the same way, the differentials of the corners. We'll also get differentials for all of these corners, but I've not written them down, and we'll also get some differentials from the internal DGA, which I've also not written down. But if you're interested, there are papers by a survey paper by Etnier and Ng, which is all about how to compute Legendrian DGAs, and then also papers by Ekholm and Ng, and also by Wikili and Edgu on how to compute these DGAs in the presence of one handles. Okay, so now what we're going to do is we're going to use this DGA to compute the symplectic homology, which by result of Bourgeois, Ekholm, and Eliashberg is a Hochschild-like homology coming from the DGA. So here is roughly their definition. You can pause the video here if you want. I will leave it here for a second. It's quite a technical definition, and I'll only briefly say what I'm doing with it in the subsequent slides. So here is the differential part. This is all adjusted to the particular case that I'm looking at. It's not terribly important to understand all of that, so don't worry. But the idea is that we're going to use the DGA to find a cycle C in this Hochschild-like homology. Sorry, in the thing that we're taking the homology of. And we're going to make sure that this cycle is not trivial and not in the image of the differential. And this will show that we have a non-zero representative in the symplectic homology. So for the 10-155 example, I'll just show you what this cycle looks like and explain roughly why it's not going to be in the image of the differential. So what we're going to do is we're going to recall that the differentials of these terms, and note that each C0 of ij term appears twice in all of these words. Okay, and what we're going to do is we're going to take an alternating sum with appropriate t coefficients so that this differential is 0. So we're going to let C be equal to t times A minus t times B3 plus B1 minus B4 plus B2. And if we compute the differential of C, this is going to be 0. The second thing to note is that these terms are all linear monomials, and the fact that the differential is 0 and that they're all linear monomials is going to mean that they are not in the image of the differential for the homology. Okay. So this is going to give us a non-zero representative in symplectic homology, which means that we can use the following theorem of Maclane. So this theorem of Maclane says that for X and W convex compact symplectic manifolds, if W is subcritical and the symplectic homology of X is non-zero, then X cannot embed in W as an exact codimension zero submanifold. So this theorem follows from Viterbo functor reality, and we're going to use it to make a contradiction. So we're going to show that if U is concordant to lambda is concordant to U, then X lambda has to embed in the four-ball, which is subcritical. And this will be the contradiction, which will give us the main theorem. Recall the statement of the main theorem is that if lambda satisfies U is concordant to lambda is concordant to U, and lambda is smoothly the closure of a 3 braid, then lambda has to be U, the max to be unknot. Okay, so the proof goes roughly as follows. If lambda satisfies U is concordant to lambda is concordant to U, then either lambda is the unknot or it's the closure of a quasi-positive 3 braid of algebraic length 2. So supposing that it isn't the unknot, then the double cover has to have a filling X lambda with non-zero symplectic homology. This follows from all the work we've done so far. Now you'll recall from the proof of lemma A, we had this construction, which was the four-ball, and we have in here embedded as a contact hypersurface the double cover sigma 2 lambda. So we can make the following exact sequence. And from this exact sequence, we say that things here are 0. And so that then we know that H2 of V is 0. And so what this means is that we can proceed. So we're going to replace X in the previous picture with our filling X lambda. So we're going to carve out X and we're going to glue in X lambda. Now this is something still with boundary S3. So it has to be a four-ball blown up some number of times. So we're going to call this new manifold W. And from here, we can construct another exact sequence. And because a whole bunch of things are 0 again, we get that H2 of W has to be 0. If H2 of W is 0, that means that W has no exceptional spheres. So in fact, W has to be the four-ball. So X lambda embeds in the four-ball, which is a subcritical manifold, and this contradicts Maclane's theorem. So lambda has to be U. So we're done with the, I should draw a square. This proves the main theorem. And I just wanted to add one more thing. So this is a corollary of the main theorem. For those who maybe are not so interested in Lagrangian concordance, you might still be interested in this for the following reason. So So if sigma 2 of lambda is the double cover of S3 branched over a quasi-positive transverse 3 braid with algebraic length 2, and lambda prime is not the unknot, then the double cover of S3 branched over lambda does not embed as a contact type hypersurface in R4, in the standard R4. So this gives us an infinite family of examples of rational homology spheres which do not embed in R4 as contact type hypersurfaces, which might be of interest to you. Okay, I think that's the end. So thank you very much for listening, and thanks again to the organizers for the invitation and for organizing this lovely conference.